My research question is about do amenities significantly predict residential property values in MS, Iowa? I have chosen four predictors: garage area, number of fireplaces, central air conditioning, number of garage cars, and the responsible variable sale price. My null hypothesis is all of their beta are equals to zero, and my alternative is at least one beta is not equal to zero. My first part of the study is to clean the data. I applied the dataset to the four amenities. I chose the end response variable only. And there are 29, 30 observations before removing missing values. After removing, there's one record is removed. Here I fitted the MLR model. The coefficient for all four predictors are statistically significant and shows a positive impact on sale price. The F-test also shows a highly significant overall model. GC and GA shows the strongest two effects. To check if GA and GC are needed to put into this model, and all reduced model confirm that they both needed to include in this model. All reduced model shows a large F values indicating that removing any predictor would significantly worsen the model.
Following step is checking diagnostics of the model. This study performs a Shapiro-Wilk test for normality. The p-value is less than 2.2 e to the negative 16, so normality is violated. For Bruce-Pagan test for heteroscedasticity, the p-value is still less than 2.2 times e to the negative 16, indicating strong heteroscedasticity. For Durbin Wilson test for independence, the p-value is zero, indicating violation of the independence assumption. For VIF for multicollinearity, the model doesn't change, so it's still no multicollinearity.
The box-Cox plot was then used to find an appropriate transformation to response variable sale price. The optimal lambda is 0.05, which is close to zero, so this study performed a log function to response variable in this model. After logging y, Shapiro-Wilk normality test changed from 0.92 to 0.97. Bush-Pagan test changed from 270 to 122, and the Dublin-Wilson test changed from 1.39 to 1.47. Although the model improves, the diagnostic test p-value remains significant. Garage cars shows a clear positive adjusted relationship, suggests GC remains a strong predictor. Fireplaces also shows a positive partial relationship. Slope is weaker but is still upward. Central air conditioning relationship appears mostly flat because it's a binary variable and much of its effect is absorbed already by the log transformation. Garage area shows a positive trend, but with substantial spread, may indicate possible interaction with garage cars or nonlinear pattern. After adding interaction, BP do increase, but not severer than before transformation. VIF increased and the VIF for GC is over 5, which is still acceptable. Finally, AV plots were examined after interaction to check whether the misspecification still appears. For the interaction AV plots, the curve improves for both GC and GA, and the relationship appear more linear. The other two predictors remain linear relationship, meaning no additional interaction is needed.
Hi, I'm Anuj, and I focus on whether the interior living space of homes in Ames, Iowa significantly predict the sales price of the house. I use the Ames housing data set. I worked with about 2,929 observations after accounting for missing values. My response was variable was the sales price, and my four potential predictors were above grade living area, basement area, and the first and second floors. I created histograms to do some exploratory analysis. We see some skewness, right skewness. Then I created a correlation matrix where we can see some strong correlations between some predictors at the end, which could hint at multicollinearity, but more on that in our diagnostics. I first fit a multiple linear regression with all four predictors on the original sales price scale, and this model had an R squared of about 0.63 and highly significant F-test, so at least some predictors clearly mattered, but the coefficient for greater living area was negative, which didn't make sense thinking when you consider that more living space should mean higher prices. So then we moved on to the diagnostics to check this out more, and we see extremely high VIF values, which indicate multicollinearity. We looked at a Bruce-Fagan test and they showed signs of heteroscedasticity, and we conducted Shapiro-Wilk and found evidence for non-normal residuals. And we found using Cook's distance a number of high influential points. Other metrics we found high leverage um, points and outliers. So the initial model violated several key assumptions, and we need to fix that before we can interpret. To address the funnel shape in the residual plot we made after the diagnostics, we refit sales price to be the log of sales price, and the Bruce-Pagan statistic dropped significantly. However, it did not disappear. To solve the multicollinearity issue, we realized that greater living area was the sum of first and second floor at minimum. So we then made two models, one with and one without. And we took the one with the lower AIC value because it contributes better for prediction. And after that, we got a R squared of about 0.61, and the all coefficients were positive significant, and the VIF values were now in acceptable range. Because of the variance and the normality assumptions were still violated, we had to do something about trusting the standard errors. So in R, I used the bootstrap procedure with about 2,000 resamples, and the 95% bootstrap confidence intervals for all three coefficients stayed entirely above zero. So the basement, first floor, second floor square footage all had significant positive effect on sales price, as you can see here. Yeah. To check how well the model does, I validated with a tenfold cross-validation. The training and actual RMSE values are very similar, so we know it predicts data well. And a sequential ANOVA was conducted to ensure that each predictor does indeed contribute something unique. And then we performed the hypothesis test since all the confidence intervals for each predictor were above zero. We knew we could reject the null and confirmed that all three predictors were significant. For the interpretation, for every extra 100 square feet of basement, about a 3.8% increase in price, 100 square feet in first floor, about a 4.2%, and about a 4.4% for the second floor. So even though some assumptions are still imperfect, using Bootstrap and cross-validation, it gives us a much more reliable inference. We can confidently say square footage does significantly predict homes prices. Interior square footage does significantly predict homes prices in Ames, Iowa.
Hello, my name is Saab. My research question for this project was how does lot size and neighborhood zoning classifications affect residential property values in Ames, Iowa? Essentially, I wanted to see whether physical land characteristics like lot area and regulatory factors like zoning have measurable effects on housing prices. To dig deeper into my research, I used the Amos to Housing dataset and kept only complete observations, which came around 2,440 rows. So my predictors included lot area, lot frontage, which basically refers to the lot and the closest boundary it is to. So, for example, a public street, road, etc. The third one was above ground living area, which is also another continuous variable. And the last one was a categorical variable, which basically what the property is classified as. The response variable is sales price. So after I was able to pick all these variables out, I was able to create descriptive statistics. So here's a couple four I've shown for the presentation. So one of the things I kind of wanted to know here was we can actually see that living area and sales price have a very linear relationship. So to get started with the multiple linear regression ship, I included all my predictors. So we can see that the model explains around 56% of the variation in sales price, and the VIF values are actually below 2, so there's no collinearity. So there's no multicollinearity. However, the residual plots and the Bruce-Pagan test show that there is heteroscedasticity, and the Shapiro-Wilk test also shows that the residuals are not, they're non-normal. So meaning like, which basically shows that variance isn't constant and it's not normal. So the next step is to stabilize these variances. To correct for the non-constant variance, I applied the log transformation to sales price, which improved residual patterns and slightly also increased the R squared to 0.594. So the log model actually reduced the spread and improved the linearity. So at this stage, I also thought lot frontage was not that significant as the p-value was around zero point 0.2. Um, and when we actually removed the lot frontage, it actually only reduced the r squared by 0.02 and did not change the adjusted r squared. So to make the model more parsimonious, I decided to remove um, lot frontage. So to check coefficient stability, I ran bootstrapping with 500 resamples. So the results showed narrow confidence intervals for most predictors, confirming that the model is robust. Uh, notably, Notably, the one thing I kind of wanted to point out was the lot area interval cross zero. So that kind of indicates that the effect is minor compared to living area and zoning, which I thought actually, which I thought initially that lot area was actually going to be more important than zoning, which kind of showed that, which is the opposite here. I also used a tenfold cross validation, which gave an RMSE of 0.27 and R squared of 0.9, which kind of shows that this model is pretty good for predictive performance and generalizability. So overall, the above ground living area was the strongest and most consistent predictor. Kind of shows that buyers value usable interior space more. This makes sense as larger living areas typically come with larger lots and also higher zone neighborhoods. Lot area did show a weaker and less stable effect, especially after bootstrapping, suggesting basically simply having more land doesn't always translate to bigger houses and also bigger housing price. Zoning, of course, remains significant because when you classify something as pretty for especially low density and floating village, these commanded higher prices, especially due to privacy and also residential appeal. Together, this results support our hypothesis that lot size and zoning influence price, but interior living space is a true driver. And of course, it kind of ties back to our lot size and zoning influence. And our final model explains roughly 60% of the price variation, with the rest likely tied to other factors.
I'm going to be addressing the research question, does the size of outdoor spaces and features predict sale prices in Ames, Iowa? I'll be using the Ames housing data set previously mentioned in this presentation. All observations will be used as there are no missing data for our variables of interest. Wood deck square feet, open porch square feet, three-season porch square feet, screen porch square feet, and pool area are 5 continuous explanatory variables that are going to be used to predict the response variable, sale price. Here is the summary of the initial multiple linear regression model. A type 2 ANOVA of the initial model shows significant marginal effects at the significance level of 0.05 for all predictors except for pool area. Both a Shapiro-Wilk normality test and a Broch-Pagan test were conducted. The significant result for both tests suggests that the assumption of normality and constant variance of residuals are violated. Influential points were identified with 214 observations having high leverage, 1 observation having high Cook's distance, and 144 observations having large studentized residuals. Variance inflation factors were calculated to look for multicollinearity between predictors. The low values indicate that multicollinearity is not an issue. Lastly, the predictor by residual plot were observed for curvature. In the first 2 residual plots, you can see strong curvature for wood deck square footage and open porch square footage. There appears to be slight curvature in the residual plot for screen porch. A log transformation of the response variable sale price was done to try to fix the normality issues of the model, and pool area was dropped from the model. The Shapiro test of the log transform model showed a slight improvement, but the residuals are still very non-normally distributed. Next, quadratic terms were introduced to the model to address the curvature of the residual plots. The quadratic terms for wood deck square footage and open porch square footage had significant effects, but the quadratic term for screen porch did not at 0.05 significance level. Next, the insignificant quadratic term was dropped from the model and a robust WLS regression was done to address both influential points and non-constant variance of residual error. The quadratic model had the lowest AIC, BIC, and PRESS statistics, indicating that it is best for prediction. Tenfold cross-validation was done to further assess the predictive capabilities of the quadratic model. the cross-validated root mean squared error value is close to the training value, and they're both low. So this suggests that the model is not overfit and can be used for rough sale price predictions. Bootstrapping was done to get a more accurate 95% confidence interval of the coefficients. The results of the bootstrapping can be used to address our hypothesis test. The null hypothesis is that the coefficients for the predictors are all equal to 0. The alternative hypothesis is that at least one of the coefficients is not equal to 0, meaning at least one does not have significant impact. From the results of the bootstrapping, we can see that none of the coefficient intervals for the coefficients contain 0, indicating that they all have significant impact, so we reject the null hypothesis. Here we have the summary for our quadratic prediction model on the right. The back transformation of the coefficients equates to a baseline sale price of about $128,000. For each of the linear terms, a 1 square foot increase equates to about a $1 increase in sale price. This makes sense as these are desirable features on homes and would add value the bigger they are. However, with the quadratic terms, there are turning points for wood deck and open porch square footage at which the impact on sale price becomes negative. Around 30% of the variation in sale price is accounted for by this model. It makes sense that this value is so low because there are many other home features that affect sale price, and adding those to the model would greatly improve prediction capabilities.
Hello, my name is Arthur, and I'm going to be creating a regression model of temporal predictors with my specific research question being, does the timing of a home's construction, remodel, or sale affect property values in Ames, Iowa? The null hypothesis for my research question will be that all predictors don't have a statistically significant effect on the model, and my alternative hypothesis will be that at least one predictor has a statistically significant effect. My predictors are year built, year remodeled or added, year sold, and month of sale. So these are just some descriptive statistics that give a bit more information about the data set. It talks about the mean, the variance, the standard deviation, and the range for the 4 predictors: price, year built, year remodeled, and year sold. It was really surprising to kind of see the standard deviation of the price as well as the lack of range in the year sold. Here we fit the model and can see that the year built, year remodeled, and month sold have a positive effect, while the year sold had a negative effect. It is also important to note that year built and year remodeled were extremely statistically significant, while year sold was barely significant and month sold was not significant. This also shows the R-squared value that says our model explains about 37.2% of the variation in price. Now we look at the correlation, variance inflation factor, and the Bush-Pagan test. The correlation shows that year remodeled and year built captured about 60% of the same information. These are the highest correlated variables, with others sharing less than 15% of the same information. Next, the VIFs are all below 5, which means there's no evidence of problematic multicollinearity. Lastly, the Bush-Pagan test looks for variance in the errors, which with a p-value this small and a BP of 98, there is non-constant variance in our errors. These are the added variable plots that show a positive linear trend in the year built and year remodeled / added. This also shows banding, which aligns with our previous assessment of a non-constant error. Quickly, this is our QQ plot, which shows clear curvature and skewness with a few outliers near the extremes. This just shows the effect that the interaction of months sold and year sold had on the model. It was unfortunately not statistically significant, but it kind of follows the previous trends with these variables. Based on the BP test and banding in the AV plots, there's clear non-constant variance in the errors. The QQ plot was also skewed, and there seemed to be some curvature in there. These can be mitigated with a log transform on the price. The table below shows the transform and that it is now explaining about 45% of the variance in the price. The BP test afterwards also shows the decrease in non-constant variance with a simple change. Since year sold was seen to be insignificant and didn't uniquely explain a large amount of the information in the AV plot, the improved method drops it and keeps months sold. This changed the variance explained to around 44.97%, a slight drop which is expected from dropping an insignificant variable. Lastly, we performed a bootstrapping and cross-validation on the improved model. The bootstrapping showed very narrow confidence intervals for year built and year remodeled, with slightly wider intervals for the intercept. The confidence interval for month sold did pass through 0, which supports the month sold doesn't have an effect on price. Next, we performed a 10-fold cross-validation, which gave us a higher RMSE for our base model, meaning our improved model does perform better on predictions for unseen data points. The final model produced an F-statistic of 797 with degrees of freedom 3, 2,926 with a very small p-value, indicating that at least one predictor significantly affected price. Specifically, sale price increased by about 0.553% per additional year built, 0.6536% per year since remodeling, and 0.4045% for each month later in the year the home was